Welcome to this tutorial of the Kratos ROM application. This is the third tutorial of the series, and in this one we're going to see how to set up a reduced order model starting from a structural mechanics simulation. In order to follow this tutorial, you will need to have installed either GID or ParaView, and this is only for post-processing. And from Kratos, we will need the structural mechanics, the constitutive laws, and the ROM applications. This is the example that we're working with, and last time we created these 4 files. In today's video, we are going to see how to use the ROM Manager class from Kratos Multiphysics. In particular, these general ROM Manager parameters, this is a Kratos parameters object that will contain all of the settings of the training and testing of the simulation. And we will call this method fit, test, ROM, and print errors methods. So these are the methods. This is what we're going to be covering in this tutorial from the ROM Manager. So if we follow this link, we will go to this page in the Kratos Multiphysics repo in GitHub, and as you can see, this is the ROM Manager class, and it has some parameters. So it has all parameters have default values. We are interested now in these general ROM Manager parameters. If we don't pass anything, let us see all of the default values that are set up with this function, set up ROM Manager parameters. And here, as you will see, are all of the possible parameters of the ROM Manager. In this tutorial, we will see a subset of these parameters. So let us go to the 4 files that GID created for us last time, and if we open the main kratos.py, we will see the standard and simulation as is, but created by GID. So the libraries that are imported here are 3 auxiliary libraries and then the Kratos Multiphysics. Then there is this function that creates an instance of this class, and what it does is just add some flushing to the standard simulation. Then in the main block, so we have all of these lines are creating a simulation object, and only the last one is launching it. That's the main kratos.py as is. What we are going to do is erase everything basically, and we are going to be using, as we said, the ROM Manager. So let us import from Kratos Multiphysics.ROM application.ROM_manager import ROM Manager. ROM Manager, and let us create here a ROM_manager object that calls this class. So as is right now, it should create a ROM Manager object with all of the default parameters. We want right now to focus on these parameters for this particular example. So let us paste this function. This function only creates a Kratos parameters object that contains these fields: ROM stages to train, and this is a list of strings. These are the possible inputs, ROM and HROM. For now, let us just keep ROM here. ROM stages to tests, let us keep it empty. Then save GID and save VTK outputs, let us keep it as true. And in the ROM field, this has this model part name. For this example, it should be structure. For a fluid dynamics example, as we will see in the next example, it should be fluid model part, and then for a convection diffusion example, it should be thermal model part. And then nodal unknowns, these should contain the degrees of freedom that are solved per node. For our 2D structural mechanics example, it is displacement x, displacement y. The rest of the example, the rest of the parameters, let us accept the defaults for now. So here, let us put here in the keyword argument general ROM Manager parameters this function. Then only to finish, ROM Manager.fit, and then ROM Manager.print errors. Right now, this is a completely fine workflow. If we just launch this, This will proceed to do the training, and it will tell us the approximation error in train set versus, so FOM versus ROM is 1.2 e to the minus 11. So we just set up and launched our first reduced order model. It was, as you can see, just a couple of lines, and exactly what we have done is this. We have launched, using the fit method, a single simulation of the full order model. This is, since we didn't specify anything else, this is the simulation already contained in the project parameters. That is 10, 10, and 10. That's the modulus of all of the pressures. Then it went and optimized inside the ROM manager and created this ROM. The same mu vector 10, 10, 10 was passed to the ROM, and then a vector was obtained. And inside the ROM manager, when we used the print errors, it showed us the validation, that is the difference between this and this vector. So the one from the FOM, the one from the ROM, and that was of the order 1.2 e to the minus 11. Why would we be interested in such a workflow? For example, if this was a time-dependent simulation, rather than having a single vector, we would have here a matrix. And this would be interesting if the FOM was expensive to compute and we wanted to create a reduced order model only using the first few seconds or minutes, and then let a FOM evolve the dynamics of our problem. We will see an example of that in the next tutorial on the fluid dynamics. For this case, we want now to change this mu vector. In Kratos, in the ROM application, we have mainly three ways of doing this to change the parameters. So in this particular tutorial, we will see how to change the Kratos parameters object that is created basically from reading the project parameters.json. This is helpful in changing boundary conditions, and right now we are going to be changing the pressure loads. So let us open here the project parameters. This file has mainly these 5 main fields: the problem data, solver settings, processes, output processes, and analysis stage. And here processes contains the in this case constraints process list is the process is the part of this file that is setting the bottom line to 0. So we are constraining here the bottom line, and the rest of the processes in this load process list contains we're setting each of the pressures to 10. So we are interested in changing this particular field. So it is within the project parameters, going to processes, then to loads process list, and changing in parameters the value of the load. We will do that using a function. So here we should create a function that changes the Kratos parameters object, and it is something like this. So this update project parameters will get a parameters object. This is a Kratos parameters object, and a list mu. So it will go to processes, loads process list, and then it tells this is the index in this list, then parameters and value, and it sets whatever is in the slot 0 of this list. Does the same for slot 1, and it does the same for slot 2, and returns the parameters object modified already. So this is a keyword argument that is expected by the ROM manager class. So that's it. Right now our ROM manager knows how to change the mu parameter, and in order for us to specify it, we need to pass it to the fit method. So we say, for example, let us create new train equals the original one was 10, 10, 10. Let us put 20, 30, 40. Oops, this is not 20, 45, 16. This is just an example. So 23, 46, 39. Let's create another one. 10, 23, 45. So of course in a bigger case, we might be interested in using a function to explore the parameter space more efficiently. The only thing that we need to keep in mind is that the type of this object should be a list. It should not be a NumPy array, it should be a list containing the lists. Each of the lists inside is representing a single case. So we pass this to this object to this fit method, and then we proceed to launch it. So using these three cases, we just launched the three cases and created the reducer model using those three cases and launched for each of the reducer models. So it passed each of these lists to one reducer model, and the difference between the outputs of the ROM and the FOM is of this order, 1e to the minus 12, 9.6 e to the minus 12. Right now we are saving everything as we specified here, both the VTK output and the GID output. We are saving it in this results folder. So this results folder contains, in this case, the results. We have 3 results for the FOM, 3 results for the ROM in both GID and VTK outputs. So we could, for example, open just ParaView to observe one of them. File, open, and we could go here. So we know that the output is of the order of 1e to the minus, 9e to the minus 12. So we are able to capture the reduced order model, the full order model's behavior with using the reduced order model. Let us put false here for now. So no, we are not saving now any results on the VTK or GID outputs. What I would like to do now is to use this test method that I mentioned. So the test method, what it does is manager.test. So once I created my reducer model using these 3 cases, I would like to test it in an unseen, in some unseen cases. For example, I could put 200, 300, 400. Let's put another one. 45, minus 20, minus 30. So this mu test, we pass it to the ROM manager dot test, and then we would be launching unseen parameters. So these parameters are not used for optimization. So only the first mu train parameters and the fit method are used for creating a reducer model. These second set of parameters are going to be used only for launching the FOM and launching the ROM, but no optimization occurs. And then I will see how well can a ROM constructed using only the first set of parameters reproduce the second set of parameters. I will see that using this print errors method. I just need to add something else here. I just need to add here in this empty list, I should put here also ROM. And now in ROM stages to test, that should do, and let us see the result. So as we can see, both of the errors are of the order of 9e to the minus 12, and since we are putting false here, no results folder was created, only this ROM data folder was created, and this one contains the data for the ROMs as we specified in this workflow. So this is what we have done so far. So we have, using the fit method and passing a mu train there, we optimized, we launched the FOM simulations that we are specifying, we collect them and optimize we use some optimizations inside the ROM manager, and right now we are using the default ones. We create the reducer model and then we launch the reducer model, and the validation was of the order of 9e to the minus 12 for this ROM for these parameters mu train. Then we did the test, but no optimization occurs. So the test corresponds to passing some parameters to the foam and passing those same parameters to the created ROMs, but no, we are not taking them into account. So these solutions are not improving the ROMs. These ROMs existed using the train method, using the fit method, and then we're validating it again, and we see the error using the print errors method. We are only missing two methods, which are the ROM manager dot run ROM and ROM manager dot ROM form. Let us even comment everything before. Right now we are only focusing on launching. We are not training, so we don't need to do any of that. Let us launch it for a vector with 300, 200, 500. That will launch a single instance of the full auto model, but it will not do any testing, any comparison. And then we can do the same for this ROM. So since we already trained and we already called this fit method, we can comfortably just launch run ROM. So we do that. Let us clear here, and let us even put true here, for example, in the VTK output and the GID output. So let us run this. Sorry, I did, yes, I passed a single list. This is expecting a list of lists. So since it is a single case, I need to put double brackets here, and now it should work. So it launched the FOM and the ROM, and we should be able to see in the results both the run of the ROM and the run of the FOM in both formats. So what that entails is that we have done this. So we pass a list of lists containing the parameters that we're interested in exploring, and it just launches them using the ROM manager with this ROM FOM method. And of course, we need to have a ROM trained, and we can do the same for run ROM. And no comparison is done here, just launching the existing reduced auto model. So this is what we have done. We have used the fit method, passing a list of lists as mu train. We have done the testing, we have done the ROM FOM, and we have done the ROM of the reduced auto model. In the following tutorial, we will see a similar workflow for the fluid dynamics case, and we will also see how to set up these material change.